Okay, so Newton's third law. Okay, so we've done the first law, which is for an object in motion stays in motion. An object at rest stays at rest unless acted upon by an outside force. The second law of motion says that the net force is found by taking mass and multiplying it by acceleration. The third law is based on the fact that forces always act in pairs. But when they act in pairs, so that for every force, there's another force that acts kind of against it, and those forces are acting on different objects. So everything we've done so far with free body diagrams has been looking at all the forces acting on one object. Now we're going to look at when there's a force acting on one object, what's the opposite force to that? So they always act in pairs, but they act on different objects. And the two forces that we're talking about here, so two forces will always be involved when two objects interact. There's an action force. So if you have object A, so let's say object A is just a box. Okay, so that's object A. And there will be an action force. So maybe, actually, let's change that. Let's make object A hand.
A what?
Hand. Hand.
Oh, nice.
Okay. And it's facing the wrong way. And it's going to push on a box. Okay. So it's going to push on a box that's B. It looks more like a foot, doesn't it? Right? Yeah, with the little thing. Okay. Okay. So the action force is will be the force of A on B. Okay? So the action force is the force initiated by object A on object B. And I just simplify that to be force of A on B.
A.
And the reaction force then is the force exerted in response by object B on object A. And it acts in the opposite direction as the reaction force. So if I push on something, right, I push the book along, the book is actually pushing back on me as well. But when we analyze the forces, we've always only just been looking at the book or just been looking at the hand. We don't look at the two objects together. So there's a reaction force acting backwards that way. And that would be the force of B on A. So just to reiterate, this is hand on box. And box foot, okay, and box on hand. I never took art in school. And the way we can write that in terms of kind of a formula, or using formulas, or like using Newton's second law to write it, is that the force of A on B is equal to the force of B on A. They're the same same size. Like this, they have the same magnitude, but one of them is going to be negative. And the way that I've drawn this up here, the one that's going to be negative is the force of, or sorry, the force of B on A is negative. So they're the same, but one is negative. And it doesn't really matter which one you make negative. And even the direction tends not to matter. It's just as long as you understand that like the forces are the same, they're just acting in opposite directions, but they're acting on different objects. Right, so if we wanted to do a free body diagram for either of these objects, then we would just be looking at just the hand or foot and just the box. Right, and that would be the free body diagram. And we have to analyze them separately if we're looking for net force and we want to find net force the way we've been finding it.
You don't use the arrows saying plus or minus? I have no idea what you just said.
Oh, the directional justification. Not so much now. Like I'll let you know. Like when we get to examples, we'll use it. I know what you mean. Like you mean this thing here? Not yet, but I mean we can put that there. But are you just fishing for candy? I'll think about it. Okay. So this can simplify more here, right? If this is to find the force of A on B, we can take the mass of B and multiply it by the acceleration of B. And that's going to be equal to the mass of A times the acceleration of A. So the one thing I want you to get from this is that when we go from the force to mass times acceleration, the object that we're talking about is the one that's mentioned last. right? So this is force of A on B, so that's mass of B times acceleration of B. This is force of B on A, so it's mass of A times acceleration of A. Okay, but the thing about this that's going to come into play here is that the accelerations are going to be different. So the acceleration of A and B will be different because the masses of A and B will be different. So, and further to that, right, a large mass will have a small acceleration. And a small mass will have a large acceleration. The actual wording of Newton's third law is that for every action force, there's an equal and opposite reaction force.
Equal?
Equal, but opposite. It's always the same. So when I push on the wall, right, like this, the wall's pushing back on me with the same force, it's just in the opposite direction.
It's just confusing because it's a wall.
Yes, yeah,
Like,
yeah, yeah. The other way of thinking about it, like if I hold this, right, there's a force of my hand up on the box, and then there's a force of the box down on my hand. What makes it, like you're right, like what makes it kind of harder to think about is when there's a significant difference between the masses of the objects. So if you think about like a ball, like or I drop something. So if I drop this pen down towards the earth, right, there is a force of the earth on the pen pulling the pen down. Oh, we ignore air resistance in this, right? So basically it's the force of gravity that pulls the pen down, right? So the force of gravity from the earth pulls the pen down. At the same time, weirdly enough, there's the force of gravity from the pen pulling the earth up. We just don't see that happen.
So always be.
Okay, so
Two
when you
forces,
drop
yeah.
it,
So if I drop it, it's going to fall down. The reason why we don't see the earth come up to meet it, and we could think that it is coming up to meet it, but the reason why we don't see the earth coming up to meet it is because there's a significant difference between the mass of the pen and the mass of the earth. Right. The mass of the pen, you can actually see that acceleration. The mass of the earth, the acceleration would be something like 6 times 10 to the negative 50, right? Like a whole bunch of zeros followed by like a 6 or something. So, but it is happening. Like that's action reaction pairs. It's just a lot easier to wrap your head around it when you're talking about things that are similar in size, right? Because you could see that when I held the box, right? Force of my hand up on the box, force of the box down on my hand. Okay, that's clear to see. Like you guys can see that. But the pen, it's the same thing. It's just that it's because there's a big difference in size. We're going to talk about that. Like we'll talk about action reaction pairs. Just Newton's third law in different words is just if object A exerts a force on object B, then object B exerts a force on object A that's equal in magnitude but opposite in direction. Okay. A way to think about it that some of you might be familiar with, because this is that area. How many of you have shot a gun, any kind of gun, BB gun, rifle, anything like that? See, not in a lot of other places you get like half the class putting their hands up. Okay, so you can laugh at my drawing again.
nice.
Okay. Okay. So what we have here is a gun, which will be object A, and a bullet, which will be object B. Sorry, I meant to put the B in brackets. So most of you know, when you fire a gun, like there's a kickback, right? The gun kicks back, right? The gun kicks back. Okay, there's a recoil. That recoil is a result of Newton's third law, because there is a force on the bullet, right? It's the force of the gun on the bullet going that way, And then there's an equal but opposite force of the bullet on the gun going the other way.
You're so mature. So mature.
Oh, I know that, never mind. Keep it on. Okay, so these forces are the same, right? But there's a significant difference between the mass of the gun and the mass of the bullet. So we're gonna write this, this way, like with these, the masses in here, right? The mass of the gun, is pretty big. So the acceleration of the gun is pretty small. But the mass of the bullet is pretty small, which makes the acceleration of the bullet pretty big. So the forces are the same, but the acceleration is different because it's a difference in masses. And that's why, like, the bullet goes quite a ways forward, and the gun will kick back a little bit. Like, and there is some kickback because there is a recoil force there. It's just not going to knock them flat.
Is that actually running?
Acceleration of the gun.
Oh, I thought it was like, what's the other one?
So if the mass of the bullet or any object is small.
Yeah, if the mass is small, the acceleration is going to be really big. If the mass is big, the acceleration is going to be really small. But the forces are equal. The forces are the same. These are equal.
No matter what.
No matter what. When you're when you're talking about like action and reaction forces, the forces acting on the opposite objects that are interacting with each other are equal but opposite. We then, when we want to analyze forces, we would look just at the gun or just at the bullet. Right? And then we can look at kind of net forces going on there. Can I go ahead to the next page?
Yeah.
Great. Okay, so we want to just in this here we want to determine the action and reaction forces in each situation. And so, the wall one was the one like Tim didn't like that one about the wall because the wall is much bigger. But there's we can do an action force and a reaction force, and it doesn't matter which one we make which. But I can say that the action force is me pushing on the wall. Right? And the reaction force would be the wall pushing on me. What you do is just call one thing A and one thing B, and it's going to be, one will be the force of A on B, and then the other one's going to be the force of B on A, which is the exact opposite.
I don't like this one.
A baseball bat is a baseball. Okay, that's similar to the gun one. You do feel it on with the baseball bat a little bit. So if we call the bat A and the ball B, then the action force would be the bat on the ball and the reaction force will be the baseball on the bat. Yeah, bat on ball, ball on bat. It's just a matter of picking what's A, picking what's B. Reaction force is A on B, reaction force is B on A. No, just write A and R. So action is you on the volleyball or your hand on the volleyball, whichever one. So we could say hand on volleyball. Reaction is volleyball in the hand. Like, you can think about it, like if you slap somebody across the face, there's a force of your hand on their face and the force of their face in your hand, which is why your hand hurts afterwards, because force hurts. This one's maybe a little more challenging just because it doesn't list two things in this situation. We'll ignore gravity for this because basically if you think about a rocket taking off, the thing that makes the rocket go up is the exhaust, like gas is being expelled at the bottom of the rocket. So, the action force would be the,
Fuel burning.
yeah, so how can I write this? Because it's not gonna be, like, so it's gonna be, let's say,
Engine forces are on.
well, the gas is, exhausted, push the rocket up. And then the rocket, pushes the gases out. That's hard, but basically, it's the gas is on the rocket on the gases. That's what I was getting at there, but I'm just trying to say, because that's actually how.
Your forces are.
Yeah, yeah. So the gases move down. Yeah, like so this is going to be. This is the force of the rocket on the gases, and then this will be the force of the gases on the rocket. Okay? And that's actually how rocket gets through space, because there is no atmosphere, no air resistance, and so it just moves forward by pumping the gases back. It doesn't need anything else. It doesn't have any tires to drive and air. Okay. And then this is the one I already mentioned. A ball falls towards the ground. So the ball can be A and the ground can be B. So the action force is the earth pulling the ball down, and the reaction force will be the ball pulling the earth up. And I said we just can't see that movement of the earth because the earth is so massive. And so there are theories that say if we kind of took everybody, if we got everybody in the world on one side of the earth and we all jumped at the same time, would you actually see the earth kind of pull up? And theoretically, yes, I guess. I think that's just kind of odd. Okay, so we'll do a couple calculation examples just to see what it is that we can do with this law. Okay. So while standing on a frictionless surface, two students push against each other. One student has a mass of 40 kilograms and the other 50 kilograms. If the acceleration of the 40 kilogram student is 0.65 meters per second, what is the acceleration of the 50 kilogram student? So now normally we would take a situation like this and we would look at the objects separately. Right, we draw a free body diagram for one student, free body diagram for the other student. We can do that if we want. Well, let's like yeah, we can do it that way. So if we look at student A and then student B. So student A will be the 40 kilogram student and student B will be the 50 kilogram student. So student A has an acceleration. So this is mass of A. Acceleration of A is 0.65 meters per second squared. And we want acceleration of B. And you have to look at these separately because the forces, the action-reaction forces are happening on different objects. So that's why we have two separate free body diagrams. We don't think about it as a system. So there's the force on A, the force of B on A goes in one direction, and the force of A on B goes in the other direction. And it's frictionless, so there's no opposing forces there. What we have to use to analyze this is the fact that this force here, so the force of B on A, is equal to mass of A times acceleration of A, so 40 kilograms, times 0.65 meters per second squared. So 40 times 0.65, which is 26 newtons. In this case, it would be negative, but we can just write back. because we don't need to worry about the negatives right now.
That was like B acting.
Yeah, that's B acting on A. Okay, the one that you list last is the kind of the one that you're calculating for. And over here, the force of A on B is equal to the mass of B times the acceleration of B. Whoops, that should be a little lowercase a. And we know the mass of B, we want to find the acceleration of B. We don't know this right off the bat, but this is equal to the force of B on A. So those are the same values. The force is the same in both cases. So then this is 26 newtons is equal to 50 kilograms times acceleration of B. So acceleration of B is 26 divided by 50, or 0.52 meters per second squared. And that would be forward. This is why, like, it's Newton's third law, which is why, like, when you guys are doing the Newton stations, right, you have the two scales, and you hold them together like this, push on either side. It's why no matter what you did, the forces are always the same. Because it's impossible to push, for two objects to push on each other and push with a different force. And it has to be the same force. Any questions about that so far? Okay? Okay. Okay, so we'll try just a slightly more complicated example. One that has three. Okay. So three boxes, A, B, and C, are positioned next to each other on a horizontal frictionless surface. Box A has a mass of 9.5 kilograms. Box B is 12.5 kilograms, and box C is 6.5 kilograms. An applied force acting on box A, so there's a force being pushed forward on box A, causes the boxes to accelerate at 1.2 meters per second squared. So now here's another thing. When they're all connected there, like when you have if I have a whole bunch of things in a row, like the box and the calculator and my pen, okay, which is a similar situation here, and I push on the calculator with a certain force, and the group of objects accelerates. All of them are accelerating at the same rate. They all have to have the same acceleration because they're all connected to each other. It's the same thing about if you've got a car pulling a trailer, they have to have the same speed, same acceleration. So the acceleration of the system that's the acceleration of everything. So everything is accelerating at that. So acceleration of A is 1.2 meters per second squared. Acceleration of B is 1.2 meters per second squared, and acceleration of C is 1.2 meters per second squared. So all the accelerations are the same. What we want to do is look at each of these separately. Like we've got three different boxes, so they all have the same acceleration, but we have to split them up into the three boxes and look individually at the forces that are acting on each box. So if we look at this, what's actually working on A, like there's an applied force acting on a foil. We don't know what that is, so we're not going to account for that in here, and we don't need to deal with that in this particular example. But if we look at what's going on when you push A, like when I push the calculator forward, the only force acting on the calculator actually besides my applied force, which I'm not talking about right now, is going to be, well, I can add that, it's just the box pushing back on the calculator. Okay, so
No, it'd be only the object is touching, right?
only the object is touching. Yeah, only the object is touching. So this is the force of B on A.
So B would have 2 forces?
Yes, yeah, B is going to have 2 forces. Now, in actual fact, A has 2 forces too, because it does have an applied force acting forward on it. Okay, but we don't have to kind of cope with that right now. Okay, B is going to have the force of A on B acting forward on it, and B is going to have the force of C on B acting back on it, and then C is only going to have force of B on C.
So we do need those arrows.
Well, this is all I'm putting the arrows on here is just to illustrate, like when you're when you are analyzing a situation like this, you have to look at each of the 3 objects separately, and you can write down the forces that are acting on each of them. Because one thing this does is this helps you figure out which one you're going to use to analyze the situation. Right? We can't do anything with this one here because we don't know what the applied force is, and we don't know what the force of B on A is. Okay? We can't do anything here because there's 2 forces here, but this one only has 1 force acting on it. Okay, so that's an easy one to analyze. So if we look at box C, then F net for box C is equal to the force of B on C. There's no other forces acting on that, right? It's a frictionless surface. So the net force on box C is just simply made up of whatever force B pushes it forward with. And we can find the net force on C by saying the mass of C times the acceleration of C. And that's equal to the force of B on C. Or B on C is what John Markowski used to say all the time. Okay. And why I'm finding this is because this is what I actually want to find. That's what I'm trying to find out. But these 2 are equal. So I can't use calculations on box B to find this value. But if I use calculations on box C, I've found its reaction force, and therefore this is the same thing. And I can find this because I know the mass of box C is 6.5 kilograms, and I know it's accelerating forward at 1.2 meters per second squared. So then the force of B on C, which is equal to the force of C on B, is equal to that.
What the frick? C's on B.
Yes. Well, and that the subscripts are just to help.
They're not.
If you can pick your own system to use to help you distinguish between the forces. And sometimes it's just drawing the objects and then listing stuff underneath. That's fine. Doing okay so far?
Yes, ma'am.
Okay. No? Yes? Okay. Next page. Okay?
Wait, what was the answer?
7.8.
I would have just gone all the way.
It's a matter of what you're trying to do is like you can't always find exactly what you're looking for, so maybe you can approach it from a like a different way. So a pull toy consists of 3 carts joined together by 2 short strings, and with a longer string for pulling attached to the front cart. If a child pulls the toy on a frictionless surface with a horizontal force of 6 newtons, what is the acceleration of the system? And then what force must each of the short strings be able to withstand? So we got two different things going on here. To find the acceleration of the system, we're going to look at the masses as one. If we want the acceleration of the system, we want to find the mass total, which is going to be 1 kilogram plus 1.5 kilograms plus 0.5 kilograms, or 3. And then we're on a frictionless surface, so there's no friction. So if we're looking at just the system, and we draw a free body diagram for the system, the only force acting on that is a force applied forward of 6 newtons. That's all of them together.
Oh.
It's thinking about it all as one,
That
right?
box.
Because it's all going to move at once. We want to figure out what it's accelerating at. Then for the second part, we're going to split it into the 3 different boxes. And this is the same way you'd analyze if you had like a train. You could analyze the force of each train car on the ones behind it. You can also analyze, like if you're pulling a bunch of kids, like if you're skating or something, you're pulling a bunch of people behind you. Like what, like, and so you guys might know of this if you've ever had to, because you guys skate, don't you? Yeah, so if you kind of, I don't know, like if you do things like where you kind of pull a big chain of people, like, and so the person at the front has to pull with a lot more force than say the 5th person back, because there's less people behind them, okay? So that's kind of what we're doing here. But this one here we'll do first, and this we just want to find the acceleration. So,
That box just
for me,
Is the total of the
the force applied thing, that's that whole system.
that's the whole thing. Like it's looking at the whole system together. Okay. So the net force on the whole system together is just made up of the applied force. So if we want to find the acceleration of the system, we just take the mass of the system and divide the F applied by the mass of the system. So F applied is 6 newtons and the mass of the whole system is 3 kilograms. So then the whole thing, each part of that string of carts is going to accelerate at 2 meters per second squared. Because we're going to need that acceleration. You need to know the acceleration of each cart in order to analyze each one individually. So this is a little different than the pushing of the boxes, right? Because, and Tim said it really well, when you're pushing on the boxes, the only force that was, like when I had the calculator in the box and the pen, the only force that acted on the calculator was the thing that was immediately touching it, right? The only thing that acted on the boxes were the things touching it, the only thing that acted on the pen was the immediate thing touching it. This is a bit different because they're attached by strings, so there's some tension there, right? So there's tension in string, like there's tension in string 1, there's tension in string 2, and there's tension in string 3. And that tension is then, like, the tension, the string 1 has to withstand the most amount of tension because it's pulling the most masses, it's pulling all 3. String 2 has a little less tension because it's just pulling cart 2 and cart 3, and then string 3 is only pulling cart 3. Okay? So that, like, so we look at this a little bit differently than boxes pushing each other because you're actually pulling masses with the string. But we still want to look at what's going on here. So how can I do this? So string 1. Trying to think of the best way to do this. Well, string 1 has to have a tension on it of 6 newtons. It has to be able to withstand 6 newtons because that's what it's pulling on.
You didn't have string.
tension on string 1?
Yes.
We're doing tension because it's not pushing, it's being.
Yeah, it's being pulled. Like it's tension, so it's a little different than when you're pushing or pulling something.
So, how do you pull it if you pushed it?
All right.
It'd be easier than
Yes.
pushing the string.
Yes. Yeah, well, because like not so much as easier. The string has to be able to be strong enough to hold, like to basically to pull all the masses along, right? Like you wouldn't pull a little red wagon with a kid in it with that little polyester string that you guys were putting on your egg things, right? You would want like a big cable or something like that, right? Or you wouldn't pull a car out of a ditch with twine, right? You need a chain. Okay. Because the car has a lot more mass, so that what you're pulling with has to be able to withstand the tension that you're pulling it with. Okay, and the tension that you're pulling it with is basically the net force that's acting on everything that comes after. Okay, so the tension in each string is equal to the net force, F net, on each string.
On each, like every string?
On each string, yes. So if we look at string 1, right, like string 1 has to pull 6 kilograms. So string 1 has to be equal to whatever it's being pulled with. Actually, I should do this the other way. The tension is actually what it's pulling like backwards, and then forwards was the applied force, right? Applied. Because you're actually pulling on that one with the 6 newtons. So that's why the tension in string 1 has to be equal to the 6 newtons.
Would the tension
6
in the
newtons.
string be less?
Yes. Yeah.
Oh,
Yeah.
I thought like when you said that they're all the same.
No. No, the tension in the second string is going to be less. The tension in the third string is going to be less. Yes, yeah.
Is that 3?
Oh, sorry, 3 kilograms. Okay. You said it first. Okay. Okay, so string 2. Okay, so if we look at string 2 has to pull 2.5 kilograms. Okay, so the tension in string 2, okay, is just at this point equal to the net force on that. So F net is equal to, or sort of tension in string 2 is equal to the net force, which is going to be the mass of 1 plus 2 times acceleration, right, which is 2.5 kilograms times 1.2 meters per second. Was it 1.2? No, 2. 2 meters per second squared, which is 5 newtons that it has to pull it. And then string. Nothing. Like it's just that's just the tension. Like there is no kind of other force. There is like a force forward on it, but we're not looking at that in terms of finding out the tension on the string. Okay. String 3. All it has to pull is the last part, which is 1 kilogram. So the tension in string 3 is just equal to the net force on the third cart, which is just the mass of cart 3 times the acceleration of cart 3, which is 1.0 kilograms times 2.0 meters per second squared, which is just 2 newtons. And I'm actually just going to leave example 4, because that we don't need to do with that. Here, 2.5. One plus 2. Oh, maybe it's 2 plus 3. Yeah, 2 and 3. Okay. So what I have for you, there's not a lot. There's only a couple questions in your workbook that are theory questions.
I'm not trying.
Sorry. So I owe you 2 candies then. And well, I also then I'll Trent a candy and so Tyler too.
Yeah.
So in your workbook, like I think there was actually a couple that you probably did. It was just sort of in the first. Can I go that? Or I like your stickers. Are those from the first day? Yeah. You pick stickers. Okay. So it's where it is here. Oh well. So nothing much in the workbook, but I have a worksheet that is mainly calculation questions. For me, and then there's the unit assignment thing. So the worksheet is just for practice, right?
Pause.